Hi, Doc Revis here. In this video, I will show you how to gather data for Beer's Law laboratory experiments. First, what is Beer's Law? Beer's Law, which is also known as Beer-Lambert, describes a relationship between the absorbance of a solution and the concentration of that solution. The amount of light absorbed is proportional to the concentration of the solution. The Beer's Law equation is shown here, where A, absorbance, equals epsilon, the molar absorptivity constant, which is also known as the molar extension coefficient, is multiplied times the path length for the instrument and the concentration of the sample being analyzed. Essentially, Beer's Law passes light through a cell containing this sample, and a certain amount of light is absorbed and the rest is transmitted. The incoming light is known as the incident light, and the light coming out is known as transmitted light. The ratio between that light is what allows you to measure the concentration. As the concentration of the sample increases, the amount of transmitted light decreases. The decrease is because the amount of light absorbed by the sample molecules increases. A Spec-20 Spectrophotometer is a popular general chemistry instrument that's used for these experiments. It is a single beam light source. So what happens? A single beam light source passes through the solution to measure the difference between the incoming incident light and the exiting transmitted light. And again, that ratio allows you to determine the concentration. In carrying out the laboratory experiment, there are two important parts. One is finding the Lambda Max. Two is constructing a calibration curve. Lambda Max is the wavelength where the absorbance is highest. It is a point at which there is the potential for less error in the data. A plot of the wavelength versus absorbance is made. Mathematically, we consider the wavelength to be the given and the absorbance that you record to be the response. So, essentially, you would take a series of wavelength data points that you choose based upon your knowledge about the sample. In this example, we chose 600 to 650, and we took 5 nanometer increments. So we would dial our instrument to 650. We would measure a point for our sample. We dial it to 615, measure absorbance, 620, 25, until we reach 650. We would take that data and we would plot it in Excel. Again, wavelength treated as the given, or at least we treat it as the set point or the known point. The absorbance is what we read, that is the response at that wavelength. We plot that data. The point at which we see a maximum in the curve is called the Lambda Max. We would then take that Lambda Max to carry out the rest of our experiments for determining unknowns. To determine the unknowns, we must construct a calibration curve at our Lambda Max. Let me repeat that. Step 1, we obtain a Lambda Max by varying the wavelength for a specific sample. So we would have this sample at a known concentration and we would measure it over the wavelengths. In this case, our wavelength was 610 to 650, and we found a Lambda Max at approximately 630 nanometers. We're going to now take that 630 nanometers, and that is going to be our Lambda Max we use to construct the calibration curve. A calibration curve is a plot at the Lambda Max by varying the molar concentrations which we consider to be the given, and recording the absorbance as the response. The absorbance of the unknown is then measured at lambda max and identified by extrapolating on the calibration curve. In other words, once we have a calibration curve, we would then measure our unknown sample at our lambda max, in this case 630. We would read that absorbance on the y-axis, and we would extrapolate across and drop down to the x-axis and read our concentration. Note that when this is carried out in Excel, we can obtain an equation for the line, and in this case we have the equation of the line shown here, where the slope of the line was 0.0045. That slope is equal to the molar absorptivity of the sample, which equals epsilon times the path length. Note that epsilon is known as the molar absorptivity constant, or molar extension coefficient. But epsilon times the path length is the molar absorptivity of the sample. Note in this presentation that this is all synthetic data. But this is a process that will be used to carry out a Beer's law experiment in most general chemistry laboratories. Many of the experiments in general chemistry laboratories are carried out using a Spec-20, which is an older instrument. The newer model is called a Spec-20D, which is a digital, but the Spec-20 has an analog readout. We show you here a brief summary of how to use a Spec-20. For more details on how to use a Spec-20, see my other YouTube video on this subject. But the first part is the initial setup, which involves turning on the instrument, setting the 100% knob all the way counterclockwise, then selecting the wavelength, step 3, and setting the wavelength switch or slit or filter to match the experimental wavelength. Once the instrument is set up, the instrument is calibrated by turning the 0% knob until the needle reads 0, putting the blank cuvette containing your blank sample in the holder, then adjusting the %T knob to 100%. Once that is done, move on to the experimental phase, where step 8 is to remove the blank and replace it with your sample. Then you would read the absorbance and record that, and then you would repeat this process for each sample. So there you have it, how to carry out a Beer's law experiment in general chemistry using a Spec-20.